This video is on normal distribution. Example 1, I'm going to do in class. We're going to start by talking about histograms. Here are two examples of what symmetric histogram shapes look like. Example 1 and example 2. But not all histograms are symmetric. The non-symmetric histogram below shows that the data seems to be more one-sided. We call these data sets that give histograms that look like these skewed distributions. So the one on the left is left skewed, which is negative skewness. The one on the right is right skewed, and that is positive skewness. If you look at the one on the left, the mean is smaller than the median and the mode, but on the right, the mean is larger than the median and the mode. To determine larger or smaller, we're not looking at the height of each of these lines. We're looking at their distance on this x-axis here. So we're looking as we go further to the right, the numbers are larger. That's why the mean is larger on this one than on this one. This example I will do in class. Normal distribution. You may be familiar with the bell-shaped curve called the normal curve. A normal distribution is a function of the mean and standard deviation of a data set that assigns probabilities to intervals of real numbers associated with continuous random variables. Here are some properties of the normal distribution. The probability assigned to a real number interval is the area under the normal curve. And because the area represents a probability, the total area under the curve is 1. The maximum value of a normal curve occurs at the mean, and the normal curve is symmetric about a vertical line that goes right through the mean. The normal curve also has a horizontal asymptote at y equals 0. A normal distribution is organized with regions that coincide with the standard deviation. The figure shows the percent of data in a normal distribution that falls within a number of standard deviations from the mean. So as we look at this diagram, as you can see my blue line here, that represents one standard deviation to the left and to the right, and that accounts for about 68% of the data. The green line is 2 standard deviations to the left, 2 to the right. That coincides with about 95% of the data. And then 3 standard deviations away from the mean accounts for about 99.7% of the data. Although the curve that we just looked like is a more accurate representation for the percent of data, we are going to use the empirical rule of 68, 95, 99.7 to estimate percentages. So as you can see here, there's the mean. So again, 68% of the data is within 1 standard deviation, 95% within 2, and 99.7% within 3 standard deviations of the mean. We're going to do this example. The following curve shows the scores for the SAT, which is designed to be normally distributed with a mean of 500 and standard deviation of 100. The shading of the graph shows 1 standard deviation on either side of the mean. Now, when I looked at your notes, the shading did not show up very well. So you might want to go in and shade it in your notes so you understand where we're coming up with the numbers. What percent of scores are between 400 and 600? Well, the mean it told us is 500. 400 is 1 standard deviation to the left. 600 is 1 standard deviation to the right. And we said, if we go back a screen, that 68% of the data occurs in that region. So our answer is going to be 68%. What is the probability that a score is above 600? Well, if we look here, again, you're going to have to shade this in your notes. This is what we're looking at right here, this yellow shaded area. Well, we know already, if I draw a line here, that from here to here, we said that accounts for 68% of the data. So if I just right now want to deal with, I'm going to highlight something. If I want to just look at this part right there, that will be, highlight this in here, that will be half of the 68%. So that will account for, right there, 34%, because that's going to be 68% divided by 2. And so if I know that this is cutting it in half, so I know that from here over to here, that accounts for 50% of the data. I only want this tail end right here. So if I take the whole right side and I subtract off the green highlighted part, which is 34%, I'm going to get 16%. That is the probability that a score is above 600. What is the probability that a score is less than 300 or greater than 700? Again, it's the shaded in the tail end on the left and the tail end on the right. Well, we know that the entire probability under a curve, we said, is 100% or 1. So if we want to find out the probability that a score is less than 300 or greater than 700, then we're going to take the whole 100% and we're going to just subtract off 95%, which will give us 5%. And the reason we're subtracting off the 95% is, let's go back. We said 95% of the data is within 2 standard deviations of the mean. So if I scroll down, 2 standard deviations from the mean is all of this stuff, all in here. That accounts for 95% of the data. So if I take the whole area under the curve and I subtract off the part I don't want, I'm going to get the part I want, which is the 5%. And what is the probability that a score is greater than 300? So we're using this same curve here. Try to do this and make it look symmetrical here. Okay, there's our 300. And we want to find the probability that the score is greater than 300. So we basically want all of that. The only thing we don't want is the tail end over here. That's the part we don't want. So again, this is cutting it right down the middle here. If I take this whole half, accounts for 50% of the data. And again, at the 300, this is 500. The distance from here to here is 2 standard deviations away from the mean. And again, 2 standard deviations away from the mean on either side accounts for 95% of the data. Well, I already took care of this half, so I just want to figure out what this half is. So I'm going to take the 95% divided by 2. So 50% plus 47.5% is, scroll down here, is 97.5%. That is the probability that the score is greater than 300. It's accounting for everything in the blue. Summary. All right, to the right is a normal curve. Each of the lines in the normal curve represent 1 standard deviation. Enter the percent of data that can be found in each of the regions. Well, we already know this. So we know that one standard deviation to the left and right accounts for 68%. So that means this has to be 34%. This has to be 34%. So that adds up to 68%. Well, I know, so I'm going to go like this. I know that. Then this, I know, needs to add to 68%, and it does. So now I'm going to deal with the 2 standard deviations away from the mean on either side. I know that accounts for 95% of the data. So adding 34 and 34, and then figuring out what's here and here to add up to 95%, this right here has to be 13.5% and 13.5%. So now if we add 13.5 plus 34 plus 34 plus 13.5, we're going to get to the 95%. Now, 3 standard deviations away from the mean on either side. This one's not letting me draw the green line, so I'm just gonna, you can see where it is. Oops, I don't want to do that. Accounts for 99.7% of the data. Let's see if I can just use my finger to draw that line here. It's not letting me do that. There we go. So adding up all of these together, including the little part in the green, this little part right here is going to be 2.35%, and the part right there is going to be 2.35%. Right there. And if we add up 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35, we will get the 99.7%. And then everything else, this, let's go to a different color here. Everything else over here and over here is going to account for the other part, so that the total area under the curve, the total probability, is going to be 100%. And I just want to fix that. That should be a percent sign. And that is it.